Okay. So, we were talking about different ways that we can estimate change. Okay, and so we've just kind of got one more problem that I want to do there, which is number 49. It must be somewhere around, oh, I don't know, page 248 or so. What is it? 247, thank you. And just talk again a little bit more about the different types of change and how changes in the independent variable can affect the dependent variable. So if somebody would read us number 49, please. Okay, so we have different types of spheres. We have an orange, a melon, must be a cantaloupe, and a beach ball. Each of those objects has a true radius. So the radius of the orange is 2 inches, the radius of the melon is 4 inches, and I'm not going to use that mark there. I'm actually going to write out inches. And the radius of the beach ball is 7 inches. We have the tape error, which is really the error in what? It's the error in what quantity? The circumference. Okay? So this is going to be error in circumference, and it's the same value, that 1/8 of an inch. And from the error in the circumference, we can get the error in the radius. And we'll talk about how to calculate that, and we'll calculate that in a minute. And then finally, we'll end up with the volume error. Okay, so I've pretty much just rewritten the table up here. And then we'll get going from there. Okay. Everybody got it? We good? I still see some writing. So the only error that I have is this tape error, which is going to be DC. So to find any of these other types of error, I'm going to have to relate them back to circumference somehow. And it would be great if I had a formula for circumference, and then I could take the derivative of both sides, and I'd have that DC on one side, and I know what that value is. So what's the formula that I have for circumference? Okay, pi times d. I'm going to call it 2 pi r because it's the error in the radius that I want ultimately. Okay. So if we take the derivative of both sides here, what am I going to get when I take the derivative of c? Well, I'm going to leave it as a differential. I'm not going to make it dc dr, but I'm going to have that dr be part of the other side. I'm going to think of it as if I'm using the chain rule. So what am I going to get when I take the derivative over here? Well, I'm going to have that 2 pi in front. The derivative of r would be 1, but then if I think about it as applying the chain rule one more time, I'm going to have the dr. So that tells me that dr is going to be what? dc over 2 pi. And what's my value for dc? 1/8 of an inch divided by 2 pi. Or I'm going to get that dr is going to be 1 over 16 pi inches. And because this is a math class, for the moment, we will leave it in terms of pi. Okay. So we can go back up here, and all of our radius errors are going to be the same. Okay, 1 over 16 pi inches. Why are they all the same? Okay, so Zoe says that because it's the same tape error, it'll be the same radius error. But what about the volume error? Do we expect the volume error to be the same for everything? We say no. Why? Anybody? Well, okay, so no, because they have different radii. And another way to talk about that or to realize that is that the error in the circumference doesn't depend on the actual radius. It only depends on the error in the radius. And when we start to do this whole thing for volume, what is volume proportional to in terms of a radius? V equals what? What does V equal for a sphere? Come on, Sarah, you know it. Pi r cubed. We need to know those things, guys. Okay. So how am I going to find my error in volume from that formula? I will, in fact, take the derivative of both sides. So when I take the derivative of v, what am I going to get? dv. And I've got my 4/3 pi. And what happens when I take the derivative of r cubed? Okay, so I get 3r squared dr. So you can see that the error in the volume is actually going to depend on what the radius is. And that kind of, I think it kind of makes sense. Okay, so let's clean this up a little bit here, and we're going to have dv. My 3's will cancel. I'll have 4 pi r squared dr. Now, since my dr is the same for everything, I can just substitute that in, right? What's my dr equal to? 1 over 16 pi, so I've got 4 pi r squared, 1 over 16 pi. Again, I can do a little canceling. I can cancel my pi's. I can cancel the 4 with part of the 16, and I end up with dv is r squared over 4. So now I want to figure this out for each of my objects. So the orange, oh, I can't get to funky colors from here. My orange shall just have to be green. Okay? So my orange has a radius of what? 2 inches. So my dV is going to be 2 squared over 4, or 1 inch cubed. Thank you for the units there, even though they were kind of hard to follow. Okay. My melon has a radius of what? 4 inches. So again, we can figure out dV. So that's going to give us 4 squared over 4, or what's that error going to be? 4 inches cubed. And finally, my big old beach ball, R is what? 7? So dV is going to be 7 squared over 4, or 49 over 4 inches cubed. And what's that going to be as a decimal? It's actually something you could figure out on your own without your calculator. What is it, Rebecca? 12.25. Good. So we can take all of those values and put them back up into the table. Okay? So if we go all the way up here, the error for our orange was 1 cubic inch, the error for our melon was 3 cubic inches, and the error for our beach ball was 12.25 cubic inches. And I always kind of think of it as you can almost think of the error in the radius as the error. It could be broken down almost into like an error for every inch. And so the more times you use those inches, the more times that error is compounded, the more times it grows. Okay. All right. We good? We got it? Okay. Oh, Sarah, go ahead. Well, so the reason that I use the circumference to find the error in the radius is that the error in the circumference was the only information I was given. So I had to find a way to relate what I was looking for back to the information I was given. If I'd been given the error in volume instead, I would have used this formula to find dr. But I wasn't. I was given what DC was, because that was the tape error, because the tape was what I used to measure the circumference. So the only thing I had was this equation that related C and R. But I had to have dr in terms of something that I'd already been told from the problem. So I made that choice based on the given information from the problem. Okay? All right, we good? Okay, so we've got another final application of linearization, which is going to be Newton's method. And the purpose of Newton's method is to find the zeros of a function by using an approximation or a guess, and then an iteration, which means that we repeat the step over and over and over again until the results that we get converge on a single answer. So we do this by, number one, making an initial guess. For where our function f of x is going to be equal to 0. And you can try using a graph. And then we use this first guess, which is this one up here, to get a second guess or a second approximation. Using my next guess is equal to my previous guess minus f of my first guess over f prime of my first guess. It looks a little weird, but the way to really deal with this is to do an example. And I think that once we go through it, it will make a little more sense. Okay. Well, solving where the derivative is equal to 0 will give me maxes and mins. It won't give me where the original function crosses the x-axis, which is what I'm looking for. The zeros of the function are where the function crosses the x-axis. It's all right. Okay. So we really haven't done anything like this before. Okay. All right. Everybody got what they need off the board? Okay. So let's do page 248, number 53. And somebody read that for us, please. Okay. So we don't really know an easy way to find the roots of this equation, the zeros of this equation, right? If it was a polynomial, if it was a quadratic, we could do it. If it was a line, we could do it. But this is a little bit different. So, like I said when I was writing out how to do Newton's method, you need to make an initial guess. And so a good thing to do is to graph the function. So if you pop that into your calculator, and of course when the zombie apocalypse comes and you don't have a calculator, you can plot it by hand, right? You could actually go make yourself a little table and then plot the points. There will still be graph paper when the zombie apocalypse comes, okay? But for the sake of expediency, pop it in your calculator and what do you get? Well, I want to know what the graph looks like. So it kind of goes like that, right? And this is 1 and that's 2. Okay, so Sarah's guess was 0.7, but just because my notes are like this, I'm going to go with my guess, which was 0.8. It will actually, yours will probably involve fewer iterations, but we'll do it this way. Okay. So this is my function, f of x. I'm going to need that because I'm going to be popping my answers into that. And I also need to know what f prime of x is. So all together now, what's f prime of x going to be? Plus 1. Again, you all have an interesting interpretation of all together now. Seriously, go watch Yellow Submarine, especially the end credits, and the Beatles will tell you how to do that. So I'm going to let x1, my first guess, be 0.8. Okay. Now, my second approximation, the formula tells me, is x1 minus f of x1 over f prime of x1. So that's going to give me 0.8 minus f of 0.8 over f prime of 0.8, which you could do with your handy-dandy four-function calculator. So what's x2 going to be? No. Not even close. Okay, but I want to know what the whole thing's going to be. Do all the math. And it is math that, again, you could do in your head if you had to. It would just take you a little while. Not in your head, but you could do it on paper. What is it? Rebecca, you must yell. I can't hear you because of the fan, because of everything. So what is it? No, it's not 107. I need 6 decimal places. I got 151. To round it? Okay. Did we all figure out why we didn't get this if we didn't get it? Okay. Okay. Excellent. So that's my first guess, or I'm sorry, that's my first iteration here. My next iteration is x3. That's going to be x2 minus f of x2 divided by f prime of x2, or, bless you, 0.693151 minus f of 0.693151 all over f prime of 0.693151. So what do we get for x3? Excellent. Okay. Now we have to keep doing this until all 6 of those digits are the same between 2 consecutive iterations. I do it 2 times in a row and I get the exact same number. So far, we have to keep going. So x4 is going to be x3 minus f of x3 over f prime of x3. And we're going to substitute that in. You work on your calculator. Everybody is furiously punching keys on their calculators. That's why I'm not talking. What'd you get, Sari? Well, read it out for us so everybody can hear. Good. Now note, we're getting closer here. Our x equals 3 and x equals 4 are only differing in that last decimal spot, that 6th decimal place. Okay? So let's go one more here. x5 is going to be x4 minus f of x4 over f prime of x4. And you work on it. Okay, so when we get to the x5 iteration, we've got the same thing as we got to x as we got in the x4 iteration. But what I want you to see is that this kind of correction factor, this adjustment factor, is getting smaller and smaller as we go through more and more iterations. Okay? And that's what's helping us get down to the value we need to get to. Okay? I think we have time for at least one more application of this. We may have to do the other one tomorrow. All right, everybody got what they need off of here? Okay. So another thing, another way that we can use Newton's methods is to approximate a different kind of root. So we're supposed to use Newton's method to approximate the 100th root of 100 to 4 decimal places. So this thing, the 100th root of 100, is going to be equal to some number x that I'm looking for. Right? That's kind of the whole point of x. That's why we introduce something like x, is because it's what we're looking for. Now, that's kind of crazy right now, but what might be the first thing you do? Not yet. We're going to do that, but what might I do first? Nope. No. The thing is ugly right now. Sari. Yeah, I would raise both sides to the 100 power because I'd much rather deal with 100 equals x to the 100. Because I know how to take the derivative of this. That's easy. And chances are I'm going to be taking the derivative because it's a calculus class. Okay. So if I turn this around a little bit and make it x to the 100 minus 100, now it's equal to 0. And now it's the same thing as finding the roots of f of x is equal to x to the 100 minus 100. And I just did that, so I know how to do that. So let's make a guess here. I'm going to guess that the root is 1. Pretty sure I'm wrong, but we're going to guess. Okay. So if f of x is equal to x to the 100 minus 100, what's f prime of x going to be equal to? 100x to the 99th. So that's my first guess. My next approximation, again, is x1 minus f of x1 over f prime of x1. So that's going to give me 1 minus what? 1 to the 100 minus 100 over what? Okay, so over 100. We could say times 1 to the 99. Okay, so that's going to give me 1 minus what? Well, negative 99 over 100. And I've got 2 negative signs, so this is really going to become what? 1.99. Okay. x3, x2 minus f of x2 over f prime of x2. So that's going to give me 1.99 minus 1.99 to 100 minus 100 times 100 times 1.99 to the 99. And what do we get? Okay. So obviously, we're going to have to keep going and do a few more of these until we get these last 4 digits to be consistent. But what if I guessed something else? What if my initial guess was 5? Well, yes. So x2 would be 5 minus 5 to the 100 minus 100 times 100 times 5 to the 99. And what would this part be? Is it 0.05? Okay, so it should have been a bigger correction, but okay. Um, so it's going to take us more iterations to get there. Okay. So it's just a matter of where your guess is. I'm going to let you go because the bell's going to ring. Like I said, I've got one more thing I want to talk about, and then we will start 5.6 on tomorrow, which is Thursday. Okay, we're not going to get through the whole thing this week. Those of you who are leaving this weekend, if you want to turn in your 5.4 and 5.5 homework, you can do that. If not, it'll be due when you come back. The rest of you, it'll probably be due like Tuesday, and we'll have the quiz on Wednesday if you're going to be around. Okay? Have a lovely day.